All right, Honor Stats. This is Chapter 4. We're dealing with Section 2, and we're going to deal with linear regression and the coefficient of determination. We looked at the original. It's called the coefficient of determination. The things that we're going to cover. We are going to state the least squares criterion. We're going to use sample data to find an equation of the least squares line. You're going to have two more formulas to memorize. Not as big as the other ones, but if you recall what we did in 4.1 with the chart that had x, y, x squared, y squared, and xy, we're going to be using the same chart. We're going to use the least squares line to predict a value of the response variable y for a specified value of the explanatory. We're going to explain the difference between interpolation and extrapolation. Okay? Interpolation is if the data is within the realm of the numbers of your graph. Extrapolation is a little bit more. Okay? When you start going outside of the data of your graph. Okay? So let me explain that a little bit more. You guys understand that these are linear? They're lines? So let's talk, negative is easier for me to talk about right now. So imagine we have a line with a negative slope, okay? A negative slope. This is our least squares line, which means as these numbers get what? What happens to these numbers? So these numbers get larger, the y gets what? Smaller. So I want to do this with an example. The more miles that I run, the more my weight goes down, correct? Yes? I want you to think about this. If I give you a crazy value for x like 100, Mr. Saxon ran 100 miles. Well, if you plug that 100 into the equation, it's such a large number that my weight could go down to like 13 pounds. Does that make sense? No, because I'm not going to weigh 13 pounds just because I ran 100 miles. So sometimes these equations lie to us only when you plug in a number on the x that's very, very large. Okay? It may not work. Same thing if we're talking about a positive, you guys. Let's say we have a line that's positive. So that means the more food I eat, the heavier I get, right? So if I choose and say I ate 50 pounds worth of food, next thing you know, when you plug it in way over here, this could be 700. No, I'm not gonna all of a sudden become 700 pounds because I ate 50 pounds worth of food. That's extrapolation, okay? It doesn't make sense. So the data that we're talking about is going to kind of stay within the realm of your x and y axis. Okay? Squared, everybody. And if you So I just explained why extrapolation beyond the sample data range might give results that are misleading. Okay? We're going to find this thing called r squared. Okay? Think about it very carefully. I'm going to show you a crazy formula at the end of today's lesson. But what did we do in 4.1? We found r. And what do you think r squared is? Yes, square r. Okay? And that's used to explain the percentage of numbers when you plug in that actually satisfy the line I'm about to teach you. So here's the first example and the only example we're going to do today. At Denali National Park, Alaska, the wolf population is dependent on a large, strong caribou population. In this wild setting, caribou are found in very large herds. The well-being of an entire caribou herd is not threatened by wolves. In fact, it is thought that wolves keep caribou herds strong by helping prevent overpopulation. So they want to know, can the caribou population be used to predict the size of the wolf population? So what they're saying in some words is the circle of life, okay? If there were no wolves, that caribou population can just keep skyrocketing to hundreds and hundreds and hundreds of thousands. They'll take over the land and eat them. So there's wolves there to control their population. So the more caribou, probably the more wolves. Okay? So So they collected some data. We're going to let X be the random variable that represents the caribou, so fall caribou population, but it's in hundreds. It's in hundreds in the Denali National Park. And we're going to let Y be a random variable that represents the late winter wolf population. So these are our caribou, and these are our wolves. So, can somebody tell me what 30 represents? How many? How many caribou? 3,000 caribou, right? Because it's in hundreds. So when we see the 30, we're using a 30 for a reason. But when we talk about it, it's 3,000. So the 66 goes with the 30. So basically, when there are 3,000 caribou, there were 66 wolves. Wolves are not in hundreds, okay? So they gave us 1, 2, 3, 4, 5, 6, 7 pieces of data, so we know N is 7, okay? So here's the data that we're going to be using for the rest of this problem. 17. Me, go back and look at the data pieces, and I want you to find the largest X, which in this case is 34, and just go one more. I don't want to use an actual data piece because I don't want you to say, well, Mr. Sexton, when there were 34 caribou, when there was 3,400 caribou, there were 79 wolves. Why would I plug in 34 again? Well, we're trying to find an estimate. So please always go one. So they took this data and they drew a scatter plot. That's the first thing we need to do. Now, I'm not real big on what they did here. I really actually don't like it because we look at the caribou. We got 34 was the largest, and I think 12 was the smallest. Let me look and see real quick. I would have done this 10, 20, 30, 40. That's how I would have done it, just so you guys know, okay? But they decided to put the little squiggle in there, so we're going to do exactly what they told us to do here. I think everybody in this class, in both my classes, understand how to plot the dots, yes? Okay, good. So the dots are there. Everyone knows what the squiggle is. Now, here's the difference between 4.1 and 4.2. 4.1, I'm going to tell you to draw the line of best fit. And you're going to be like, I think it's here. And that's it. You're done. The only way you're going to miss 4.1 is if you do something like this. Come on, guys. You can see this has a positive direction, and this line would definitely be wrong, okay? But today, we're going to learn how to find the exact line. Exact. Okay? So we're going to come back to this guy in a moment. Where are you at? There you are. So, y hat is equal to 22.44 plus 1.60x. That, ladies and gentlemen, is our equation for the least squares line. I do not want you to use the slope-intercept method of graphing. Let me explain why. Because there's a really good chance, ladies and gentlemen, of having a squiggle wrinkle within one of the axes. So I want to tell you right now, if you were trying to plot 22.44 on the y-axis, do you see the dilemma that you would have? Yes, there would be a big dilemma. So therefore, we don't know when that is going to occur, so we want to prevent that from happening every single time. So we are not going to use slope-intercept method to graph it. You must use what I'm about to do right here. So there is always one point that is guaranteed to be on the least squares line. And ladies and gentlemen, it is X bar, Y bar. It is guaranteed to be on your least squares line. You cannot guarantee an actual data point to be on your least squares line. This guy will. It will be there. So let's 25.1 and 62.6. So yesterday, Jordan answered a question that said, what denotes a line? You said 2 points. Here's going to be one of the 2 points that you must use. So let's go over 25.1, which is about right here, and go up to like 62. So it's going to be about right here. Okay, give or take, but we're pretty darn close, okay? Let me explain the difference between those red dots and that blue dot. The red dots are actual physical data pieces. The blue dot is a guess. It's about, but it will be on the least squares line. Everyone good with that so far? Now, this is where I vary with the book. The book says, I want you to find another point. Everybody knows how, if they were given an equation, to find another point. You get to arbitrarily choose any value of x that you want, plug it into the equation, and get a corresponding y out. Got it? You definitely can do that. But I don't like using a data piece that's already there. So this is what I ask my students more. Okay? So part 2. You must find one other point. Use, or let me just find the largest data piece and go one more. So ladies and gentlemen, the largest data piece was 34, and I want you to do this. I want you to take the formula 22.44 plus 1.60 and plug in that 35. And we're going to do that little problem. 22.44 plus parenthesis 1.6 times 35. Ladies and gentlemen, this yields 78.44. So if you think about it very carefully, we plugged in a 35 and we got 78.44 in return. Please plot that point. Here's 35 and 78 is about right here. And then what you're going to do is you're going to draw a line through the 2 points that you found. And that, without a shadow of a doubt, is the best line you could ever draw, where the sum of the squares of those points are closest to him. Okay, so here are the 2 points. X bar, Y bar, and then this guy right here is the one more than the data piece. Okay. So let me talk real quick about interpolation and extrapolation. Interpolation says if you choose any number within this realm, like say 27, if I said, if there are 2,700 caribou, could I use this formula to predict how many wolves there should be? The answer is yes, because we are within the realm of the data pieces they gave us. This is called interpolation. Extrapolation is way over here, like 100 for the value. If there are 10,000 caribou, if I plug that number into the formula, I would get 182.44. That means if there were 10,000 caribou, there's 182 wolves. Doesn't make sense. You don't know what's going to happen after this picture. So anything past your data is extrapolation, and extrapolation is incorrect. Interpolation correct, extrapolation bad. Okay? And now, so does this data indicate a linear relationship? We think it does. We think there's a positive relationship to it. We're going to find an equation of the best fitting line, but we're going to get into a little more detail. Remember what the one, I can actually, let me pause. The first step in answering these is to express the relationship as a mathematical equation, okay? We have an x explanatory and a y a response. Were 5 points. This right here are our least squares criterion. What this is, ladies and gentlemen, is this. That blue line right now is a line of best fit. You guys can draw however you want. I bet you if I took the same piece of paper and I gave everyone the same piece of paper and I told you to draw a line which you think is the best fit, and I kind of put them on top of each other, I bet y'all see a little bit difference in every single person's, okay? The one we're looking for, listen to my words, has the smallest difference of the data piece and the line of least squares. So look at that distance, look at this distance, look at the distance, look at the distance, 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 and distance. Those distances, you guys, has to be minimized. We can't use just the distances because of this. Being that this point is above it, its distance would consider to be positive. This guy is below it, his distance below it would be negative. Well, guys, if you had a bunch of positive numbers and a bunch of negative numbers and combine them, they would cancel each other out. So we really wouldn't see the true distance, okay? We're looking for a true distance. So the way we get around it is we square. This is why it's called the least squares line. We are trying to find, let's see if this makes sense. We are trying to find a line that when you write it, all of the distances that these points are away from it, we got to find the line that minimizes, that has the smallest square distances in between. Listen, that's a lot of work. That's a lot of work. Therefore, we have a formula that's going to help us out. Okay? And the least squares line. So our least squares criterion, the sum of the squares of the vertical distances from the data points, x and y, to the line is made as small as possible. Can you imagine if I gave everyone this and you had to take the piece of paper out and you drew a line and then I made you measure each of those distances? Whichever one of you 37 people had the smallest one, you would have the correct line, or the most correct line. Okay? Well, I kind of explained here. As a result, the sum, that d value, can be small enough that the points are widely spread in the scatter diagram. However, the squares cannot be negative, and that's why we minimize using the squares. All right, if we don't, the negative values and the positives will cancel out. All right, so that's a so D, well, I guess that's why we're finding a least squares line. Here is your formula. Y hat, ladies and gentlemen, is equal to A plus BX. You see, it looks like Y equals MX plus B. I know the after the equal sign is in a different order, but it still means the same thing. Would anybody like to tell me what the B stands for in Y equals MX plus B, or in this case? Slope. That is our slope. It most certainly is. And what is our A? Y. That is our Y-intercept. This thing is called a hat. It's called Y hat. Ladies and gentlemen, it is our predicted value. It's not Y. Y is an actual point. X is an actual point. Y, we're predicting what the Y is. So in our example dealing with caribou, remember caribou is X and wolves is the Y. When I plug in a number for caribou, a made-up number, I think there's 2,500 caribou. That's a 25. Plug it in. It's going to tell me how many wolves there should be. Not how many there are, should be. Why? Because we're predicting this. The equation of our least squares line. So, here we go. I hope these 5 things look familiar to you. Sum of x, sum of y, sum of x squared, sum of y squared, and sum of xy. Well, yes, Mr. Saxon, that's what we did in chapter 4.1. And this is how 4.1 and 4.2 are going to come together. You're still going to have to do that chart. You still are going to have to find r. Because at the end of my lesson today, we're going to find what r squared is. So in order to get all of the stuff we're doing in 4.2, you have to do everything in 4.1. But here's the deal. Our slope, which is in this form is denoted by the letter B, has this formula. We know what n is. We know that this is the fifth column sum. We know that this is the first column. We know this is the second column. We know what n is. We know that this is the third column sum. We know this is the first column sum being squared. You have it all in that chart. That, ladies and gentlemen, will find our slope. So if you think about it, our formula is y hat is equal to some number plus or minus some number x. You're going to find that b first. You must find this first. You must find the slope first. Why do you have to find it first? Well, let me tell you. The second thing is the a. That is the number that goes here where I just put that star. The reason we have to find that is because notice in the formula, the b is used. So what you find in that first step, b is going to be used in the second step to find the y-intercept. Does anybody know what y bar and x bar are? Those are the means. So we also have to find the means. And with all of those pieces of information, we are going to draw or write the equation of a predicted line for the wolf and caribou problem. So here we go. I'm not going to go over these, but we're going to use them. 3,000 caribou, 66 wolves, 30 squared, 66 squared, 30 times 66. Everybody in this room has the ability to find each of those. What do we need? We need the sum of all of our x's, 176. We need the sum of our y's, 438. We need the sum of the x squares, 4628. The sum of the y squares, 28026. And we also need the sum of the x times y's. I'll come back to this table as we go. You actually have that number here. You have those two sums, 176 divided by 7 and 438 divided by 7. So you don't have to search for things. Once you do this chart, it's all there. Go back to XY sum, 1133. There's my 176 and my 438. Go back, the sum of the x squares is 46. On your calculator, there's somewhere. What we are going to find are our means, x bar and y bar. Well, think about it, guys. Remember, x bar is the sum of all the x's divided by n. So I like one decimal place. So everyone, we're going to go 25.1. And we are going to go 62.6. Everybody knows that means go to 1. Means go to 1. So I'm changing the book right as we do this. Okay? And now, let me pinch this open so we can see this a lot better. The first thing we have to find, everybody, is B, the slope. There's our formula. N is 7. XY sum, 7. There it is. I put a minus sign because the formula tells me to. And then I have my first column and my second column respectively. 176, 438. I remember my n is 7. I have my sum of my x squared, 28. Notice I plug it in. I put a minus sign. And then this guy right here is my sum of my x's, which I know is 176. But this time I'm going to square it. I actually like how the book does this. This is one of the first things that I like. So higher denominator. They do the entire numerator. Whoopsie. Plug later. Back a couple till I find y bar. It is 62.6 times 25 point. Okay, 25.1, 62.6. 20. Whoops. Watch when they do it. They do the entire numerator, and they do the entire, and get 2271. Plug the denominator into your calculator, you get 1420. When I plug it in, I get 1.599. That is 1.60. We now have our B. 1.60. 2 decimal places for B and A. While we're here, let's finish it. We must find A. A is y bar. Take away B times x bar. So y bar, let me go, 62.6 minus B, which I just found to be 1.60, 25.1. Okay. Pulling out my calculator, I get 62.6 minus parenthesis 1.6 times 25.1. It yields, well, I need squiggle, it is 22.44. So, with this piece of information and this piece of information, this, ladies and gentlemen, is your exact least squares line equation. It is y hat is equal to 22.44 plus 1.60x. That is the problem, that is the least squares equation for the problem that deal with caribou and wolves. Okay, so here's our equation. Explaining the slope real quick. This is our caribou. Normally we choose the value of 1, but we know the caribou's in 100s. So normally I would say for each 1x, but since this is 100, for each 100 caribou, there will be 1.6 wolves. That's what this equation is saying. And our y-intercept kind of says this is where we start. Okay? Now, we're going to take this equation and we're going to use it to graph. This is part of the book that I actually like how they do it up to a certain point. Okay? So, remember that equation, 2244, 1.6. Let's go back. Coefficient of determination. Here's our last thing. The coefficient of determination is denoted by r squared, which is the square of our sample correlation coefficient, which we found in chapter 4.1. I can go through all of the detail. We can show you what it is. We can show you the formula for all of the total deviation. We have to square, and we get this nasty formula. No. Hey guys, you're already going to find r. So whatever r is, just square it. So, in this particular problem of the wolves, the r is 0.9. When you square it, you get 0.81. All I want to do is read what it means. We can say about 81% of the variation behavior of the y variable can be explained by the corresponding variation behavior of the x variable when we have this least squares line. So all it's saying is this. 81% of the time when you interpolate, so we're within the data, it will be true. Meaning 2,700 caribou, and it works out exactly how many wolves there are. 81% of the time when you plug the numbers in, it'll be true. Which means 19% of the times it'll be what? False. So, in a sense, we're 81% confident that this least squares line will tell us how many wolves there are when we know the number of caribou. And that's the explanation of R squared. And that, ladies and gentlemen, is chapter 4.2.